Hey there! In this video, we're going to learn about inverse Laplace transforms and how we can use a Laplace transform and its inverse to solve an initial value differential equation problem. So first thing we need to know is how to find what are the inverse Laplace transforms. And we already looked at the definition of a Laplace transform and tables of formulas for Laplace transforms. So the inverse is really just flipping the expressions. So the inverse, I'm going to use that inverse symbol with my curly L. So L with a -1, it looks like an exponent there. And so that means I'm taking the inverse Laplace transform. And before, the Laplace of 1, for instance, was 1 over s. So Laplace inverse of 1 over s gets us back to 1. So just like with any inverse, these inverse Laplace transforms, they reverse a Laplace transform. So these are the formulas for the main ones that we'll run into. You can find tables of more online. Okay, so let's do an example just to make sure we got this idea of how to apply one of these formulas to an expression or function. So I want to find the inverse Laplace transform for 5 over s squared plus 36. So I look at my table and I'm looking for a Laplace transform that looks similar to this. And the one that looks most similar is for sine of kt. So if I take the inverse Laplace of k over s squared plus k squared, that will give me the sine of kt. And so in this problem, I'm going to set this up. I want to take the Laplace inverse of this. And the k's don't quite match up, so I'm just going to have to tweak this a little bit to make it look like the formula. See, looking at the denominator, the s squared plus 36, I know that the k is going to be the 6 that I get from square rooting that 36. And so I'm going to pull the 5 out in front of my inverse Laplace. And now I have a 1 over s squared plus 36 inside, but I need it to be k, where k is 6. So I can multiply this by 6 over 6. So I'm really just multiplying by 1, but that is going to give me a 6 in the numerator inside this inverse Laplace. So I now have a 5, 6 out front. I left that 6 from the denominator outside and moved the 6 from the numerator inside of my inverse Laplace. So I have something now that matches the formula perfectly. And I get 5, 6 times sine of 6t for this. So this is just one way that you might have to adjust the expression for an inverse Laplace to make it fit the formula and get it to work. We'll see other examples as we work through this video where we have to do things like a partial fraction decomposition to break up some fractions so that I can use or find the inverse Laplace. Okay, so there's one other thing that we need to know how to do before we can start solving differential equations using Laplace transforms. And that is if I take the Laplace transform of a derivative, which we're going to have to deal with derivatives in a differential equation, I need to be able to come up with some expression for that. And so it turns out as long as f of t and its derivatives are continuous and of exponential order and are piecewise continuous as well, then that means they meet that criteria of they will have a Laplace transform and I can use this. So if I have the nth derivative of f of t and I want to take the Laplace transform of that, I'm going to use this formula. So I get s to the n times capital F of s minus s to the n minus 1 times f of 0 minus s to the n minus 2 times f prime of 0 and so on until I get all the way down to the end where there's no s anymore. So notice that with each term, the power of s, it starts with whatever the degree of the derivative is, and it goes down until I get to s to the 0, where it doesn't even show up in that last term. And at the same time, that first term gives me f of s, so the Laplace of f of t, and then all the other ones are going to be an increasing degree of derivative for the terms. So f of 0, then f prime, then f double prime, and so on, all the way until we end up with that s to the 0. Okay, so that's what we're looking for when we're using this formula, and we're going to need this when we are applying a Laplace transform to a differential equation. So let's just do an example where we do this part before we get into a full example of solving a differential equation. So I want to find the Laplace transform of the fourth derivative of f of t. We're just plugging in 4 to this formula to see how it plays out in an actual example. Okay, so there's our formula again. Here we have n equals 4. So I'm going to do the Laplace of the fourth derivative of f. So that first term is going to be s to the fourth times f of s. And then the next term, I'm going to lower the exponent on s. And then I'm going to plug in that f of 0. So I get minus, and they're always subtracting after that first term, s to the third times f of 0. And then I'm going to keep going down a power until I get all the way to s to the 0. And then I increase the derivative with each term. So minus s squared f prime of 0, minus s to the first times f double prime of 0. And then finally I get to s to the 0 power, so the s isn't showing up anymore. And then that's going to be f triple prime of 0. So that's how we're going to apply this to any derivative that we run into in a differential equation. Okay, so our strategy for solving a linear differential equation using a Laplace transform. We're always going to be doing this with initial values. So there are initial value problems that we're dealing with, and it's because of that last thing we just looked at, where I have f of 0, f prime of 0, and so on. I need the initial conditions to plug values in there when I'm solving one of these differential equations. So my strategy is going to be to first apply the Laplace transform to each term of a differential equation on both sides of the equation. And then after I've done the Laplace of those derivatives, I'm going to have some places where I can plug in the initial conditions. And then I'm going to solve this for y of s. It was f of s in our general formula on the previous screen. We're going to call it y of s because at the end of the day, we were trying to find y of t. So we're going to solve for y of s. And then we're going to apply the inverse Laplace transform to get y of t from this. All right, so it's not too bad of a process. Solving that y of t and applying the inverse Laplace transform tends to be where the most of the work comes in those last two steps. So let's look at an example where we have to go through this. Okay, so I have this initial value problem, y double prime plus 3y prime plus 2y equals 4t. And I have the initial conditions y of 0 equals 4 and y prime of 0 equals 0. So this is a perfect example of where I can use a Laplace transform. Notice that it does not need to be a homogeneous differential equation for us to use this method. There can be a 0 on the right side of the equation, but as long as I can find the Laplace of that function on the right, it doesn't need to be homogeneous. Okay, so first step, apply the Laplace transform to all 4 of these terms on both sides of the equation. Okay, so I'm going to do the Laplace of y prime, double prime plus 3 times the Laplace of y prime plus 2 times the Laplace of y equals the Laplace of 4t. Okay, so first off, that Laplace of y double prime. So my n here is 2 using that formula for the Laplace of a derivative. So I'm going to have s squared times y of s minus s to the first times y of 0 minus y prime of 0. So I only needed 3 terms for that second derivative to get down to an s to the 0 power on that last term. And then for the second one, that's going to be 3 times the Laplace of y prime. So that's 3 times s y of s minus just y of 0. So I only needed 2 terms for that first derivative. And then the last one, just the Laplace of y, well, that's just y of s. So we get plus 2y of s for that last term on the left side. And on the right, I had to use a formula to find the Laplace of 4t. And so the 4, I can just pull out front. The Laplace of t is going to be 1 factorial over s to the 1 plus 1. So 1 over s squared is what we get on the right side there, times that 4. Okay, so you can see now I've got this to a point where I can plug in my initial conditions. I've got y of 0 and y prime of 0 showing up in a few places in this differential equation now. And so I can plug those in. So wherever there's a y of 0, I can plug in a 4. And wherever there's a y prime of 0, that just becomes 0. So I end up with the equation s squared times y of s minus 4s plus 3s y of s minus 12. So I took the 3 times in minus 4. Plus 2y of s equals 4 over s squared. Okay, so at this point, I want to start collecting terms. I want to solve this for y of s. So I've got that minus 4s and the minus 12 on the left side. I'm going to move that to the right side of the equation. And then the 3 terms left that have a y of s in them, I'm going to factor that y of s out of it. So I end up with y of s times s squared plus 3s plus 2 equals 4 over s squared plus 4s plus 12. All right, so I've just kind of separated things out. And now I'm going to solve for y of s by dividing by that quadratic I have multiplying by it. So all three terms on the right side are going to get divided by that s squared plus 3s plus 2. And so I'm going to split that up into two fractions. So y of s is equal to 4 over s squared times our quadratic plus 4s plus 12 divided by that quadratic. You can split it up into 3, but it just creates more work to do so. So that's why I kept those last two together. Okay, so what I want to do with this resulting equation is apply the inverse Laplace transform to it. To do that, I need to break up those fractions on the right side. I don't have any Laplace transform formulas for these particular fractions, but I do have factorable denominators, so I can use partial fraction decomposition on each of these fractions to break them up into smaller fractions that will match some of our inverse Laplace formulas. Okay, so this is where the bulk of the work comes in, is I got to do partial fraction decomposition twice, once for each of these fractions. All right, so I'm going to start with the second one, just because it's a little easier. And I'm going to use a bit of a cheat here. I'm not going to use the system equation method to solve it, because this is a little bit faster, and this is already a long problem. So we're gonna do a little bit of a shortcut when we solve this. Okay, so breaking up that fraction on the right, the 4s plus 12 over s squared plus 3s plus 2. Well, that denominator does factor to s plus 2 times s plus 1. And since I have two linear factors on the bottom there, then that means this fraction is going to decompose into some constant a over s plus 2 plus some constant b over s plus 1. So I just need to find a and b so I can split this up, and then I'll have two fractions that I can apply an inverse Laplace to. Okay, so to do that, I'm going to multiply by the common denominator across all three fractions, and so that's the s plus 2 times s plus 1. So all my fractions get wiped out, and I just get 4s equals a times s plus 1 plus b times s plus 2. Okay, so this is where the cheat comes in. Normally you would collect those like terms and solve a system of equations to find a and b. A shortcut to that is we plug in values for s that will cause one of these terms to cancel out and allow me to solve for the other variable. So for instance, if I let s equal -1, well, then the s plus 1 that's multiplying by a is going to become 0, and I won't have to deal with the a. I can solve for b. So that's what I'm going to do. Everywhere across this whole equation that there's an s, I'm going to plug in a -1. And then I'm going to simplify it. So I end up with -4 on the left. The a term zeroes out completely, and I get just b times 1. So b equals -4. So it's a very quick way to find that, that variable. And now if I want to find a, well, let's choose s equals -2. And this time it'll zero out the b term and allow me to solve for a. So if s equals -2, and I plug that in everywhere, I'm going to get a -8 on the left side. The b term cancels out, and I have a -a equals -8, which means that a equals 8. So pretty quickly, I found a and b, and I can rewrite my fraction as this decomposed set of fractions, 8 over s plus 2 minus 4 over s plus 1. Okay, so now I've got to do the same procedure for the first fraction, which I held off on this one because it has more factors. It's going to be more fractions that I have to break it down into. Okay, so for this one, I've got a repeated factor in that s squared. So I'll break that up into a over s plus b over s squared. And then I'll have a fraction for each of the other factors. So c over s plus 2 plus d over s plus 1. Just like before, I'll multiply across the entire equation by that common denominator that's on the left side. And it gives me this lovely equation. So I have 4 times as times s plus 2 times s plus 1 plus b times s plus 2 times s plus 1 plus cs squared times s plus 1 plus ds squared times s plus 2. Okay, so again, I could solve this using a system of equations. I've got 4 unknowns to find, so that would be quite a bit of work. So we're going to use the trick where we plug in values again. So the first one that jumps out at me is if I let s equal 0, 3 of these terms are going to zero out because 3 of them have an s or an s squared in them. So that's the first thing I'm going to do is let s equal 0. And so everything zeroes out except for the b term. And I get b times 2 times 1 if I'm plugging in s for 0. And so that means that 4 is equal to 2b. Dividing by 2, I get b equals 2. Okay, so now looking at my factors again, I'm going to choose s equals -1. And that's going to zero out in all of the terms except for the term with d in it, because that's the only one that doesn't have an s plus 1. So this is going to simplify to 4 equals d times -1 squared times -1 plus 2. And all of that on the right side ends up just simplifying to 1d, so d equals 4. And if I keep going, well, if s equals -2, that's going to zero out every term with an s plus 2 in it. And so this will allow me to solve for c. I get 4 is equal to c times -2 squared times -2 plus 1. And so that's going to be a -4c is equal to 4, which means c equals -1. Okay, so far this method has worked out great. I found 3 of my 4 variables, but I'm kind of stuck at this point because I've multiplied by all the things that would zero out most of the terms, and I never got the chance to solve for a. So luckily I have all the other variables, so I can pick any value for s this time and then plug in b, c, and d as well into this function, and that'll allow me to solve for a. I just can't choose any of the values I've already plugged in because those all zeroed out my a term. So I'm going to go with the simplest thing I can think of that's not one that I've used, and that is s equals 1. I'll plug that in along with b, c, and d, and it looks something like this. Whew. Okay, so we plug all that in and simplify all of our numbers. So I end up with 4 equals 6a plus 12 minus 2 plus 12 from each of those terms. So I clean that up a little bit. 12 minus 2 plus 12 is going to give me 22. And if I subtract the 22 and then divide by 6, I end up with a equals -3. So I have all 3 of my coefficients now, or sorry, my numerators, and I can break up that big fraction into -3 over s plus 2 over s squared minus 1 over s plus 2 plus 4 over s plus 1. And finally, I'm ready to apply that Laplace transform to my equation. Okay, so going back to the equation we had, I now have y of s equals all of those partial fractions I got from decomposing both fractions. And I do notice that I have some like fractions here that I can combine. They have the same denominator. So there's a 4 over s plus 1 and a minus 4 over s plus 1. Those cancel out completely. And then I have a -1 over s plus 2 and an 8 over s plus 2. So I can combine those to get 7 over s plus 2. So it simplifies a little bit, and oh, there's an extra negative in there that I forgot to delete. So that should just be plus 7 over s plus 2. And now I can finally apply the inverse Laplace transform to all of the terms. I'm doing this also on the left side to the y of s to get me my final answer, y of t. Okay, so if I apply the inverse Laplace to every term here, I went ahead and pulled all the coefficients out of those inverse Laplaces. So I'm going to get y of t on the left side. That's what I get from the inverse Laplace of y of s. And then I'm going to look back at my table of formulas to help me remember how to do all these inverse Laplaces. And so the formulas that apply here, I've got 1 over s, and so that one's going to give me a 1. 1 over s squared, that's the n factorial over s to the n plus 1. And so here, that's going to be where n equals 1. And then the last one is going to be an e to the at. So I end up with -3 times 1 plus 2 times t plus 7 times e to the -2t, because a here in that formula was -2. And there is my solution to this differential equation.